Have you ever wondered what happens when human knowledge just breaks? Welcome to this explainer. We're going to dive into how the concept of infinity is basically the ultimate bug in the source code of reality. For centuries, humans have tried to pin down the infinite. But the moment we try to mathematically capture it or apply it to the physical universe, things get ultra-complex very quickly. Today, we're looking at the exact boundary where human knowledge, and the universe itself, stretches to its absolute limit.
Here is our roadmap for navigating these ultra-complex edges of human knowledge. We'll start with the boundary of infinity, look at different sizes of infinity, tackle quantum infinities and renormalization, map out the shape of the cosmos, and finally, look at the end of everything.
All right, kicking things off with Section 1, the boundary of infinity.
So back in 1655, the English mathematician John Wallis gave us the infinity symbol. But here's the thing, it's not just a giant number. It's really a qualitative state. It's a conceptual threshold where normal rules just completely go out the window. At infinity, the difference between a whole set and its individual parts just dissolves. And when we try to plug this limitless concept into our ultra-complex physical models, well, it forces us to deal with absolute extremes, transforming the specific and finite into the universal and absolute.
Moving right along to Section 2, different sizes of infinity. Because, spoiler alert, they are not all created equal.
To really wrap our heads around this, we have to jump back to the 1870s. The German mathematician Georg Cantor basically shattered human intuition with his continuum hypothesis. He proposed this totally mind-bending idea, that there is no size of infinity that exists strictly between the infinity of whole numbers and the infinity of real numbers. By the year 1900, this was officially dubbed one of the great, supposedly unsolvable mysteries of math.
Think about the contrast for a second. You can count whole numbers endlessly. 1, 2, 3 forever, right? But you literally can't even begin to count real numbers. Why? Because between any 2 points, there's an infinite, continuous ocean of fractional decimals. Cantor actually proved that this uncountable infinity of decimals is mathematically, fundamentally larger. One infinity is genuinely bigger than another infinity. Mind-blowing, right?
Decades later, a mathematician named Paul Cohen cracked this wide open using an ultra-complex technique called forcing. Imagine adding a mathematical wildcard to the universe, a generic real number with absolutely no specific properties. It purposefully avoids any rigid definitions, just to bypass the rules of the model. It was this wildly abstract loophole that made logicians literally slap their foreheads.
Okay, let's get into Section 3, quantum infinities and renormalization. This is where infinity completely shatters quantum theory.
When we step out of pure math and into physical reality, infinity turns into a massive roadblock. Take a bare-point electron in quantum electrodynamics. It's swarming with these virtual particles that are constantly popping in and out of existence. If you try to calculate the self-interaction of this electron using classical math, its electrostatic mass and charge just spiral into impossible, divergent infinities. What does that actually mean? Well, it would have infinite inertia. An electron could literally never be accelerated. It couldn't move. The entire universe would just be completely frozen.
This mathematical crisis frustrated the absolute greatest minds in physics. Pioneers like Paul Dirac and Richard Feynman absolutely despised the mathematical gymnastics they had to do to fix it. Feynman actually famously called it a Dippy process and hocus pocus because it prevented them from proving that their own theory was actually mathematically self-consistent. So, to save physics, they came up with this two-step mathematical magic trick called renormalization to basically tame that infinite quantum field cloud. Step 1 is regularization. You temporarily modify the theory, sometimes literally pretending the universe has fractional dimensions just to make the infinite integrals finite. Then comes Step 2, subtraction. You redefine the unobservable bare mass to be infinite itself so the two infinities literally just cancel each other out. And what's left over? The finite, real-world mass that we actually observe in the lab.
For a long time, this kind of felt like sweeping embarrassing infinities under the rug. But thanks to physicists like Kenneth Wilson, we realized it was actually revealing a deeply ultra-complex truth. Through what are called renormalization groups, we now understand that physical constants physically change across different energy scales. The universe fundamentally operates differently at the microscopic quantum scale than it does for us at the everyday macro scale.
All right, zooming way out, let's hit Section 4, the shape of the cosmos. On the macro scale, infinity dictates the very shape of our universe. In 1922, Alexander Friedman took Einstein's equations and realized that whether space loops back on itself or just goes on forever hinges on an incredibly fragile threshold. It's called critical density. And when I say fragile,
I mean it. We are talking about the equivalent of just 5 or 6 hydrogen atoms per cubic meter of space.
Basically, density determines destiny. If the actual density is greater than the critical density, meaning omega is greater than 1, space has positive curvature, kind of curving into a closed finite sphere. If it's less, it opens up into a negative curvature, like an infinite saddle shape. And if it perfectly matches that critical density, space is perfectly flat, stretching on without any limit, like an endless plane.
For decades, we thought that was the whole story. But then, in 1998, everything flipped. We discovered dark energy. This is an unexpected, completely mysterious, repulsive force that isn't just expanding the universe, it's accelerating it. It's actively pushing the cosmos apart at an ever-increasing rate, totally defying those earlier static models and driving reality toward terrifying new infinite limits.
Which brings us to our final section, Section 5, the end of everything.
So how does the infinite finally dictate the end of everything we know? Well, no matter the scenario, infinity is waiting at the finish line. In a big freeze, the universe asymptotically approaches absolute zero, hitting an infinite, maximum state of entropy. In a big crunch, gravity collapses space all the way down into an infinitely dense singularity. And in a big rip, the expansion rate, the Hubble constant, literally reaches infinity, tearing apart galaxies, stars, and eventually disintegrating elementary particles themselves.
Notice the incredible contrast here. In pure math, infinity is this beautifully structured truth. It's a rigorous hierarchy of sets and coordinalities governed by solid axiomatic laws. But over in physics, infinity is basically a flashing red warning light. When a physics equation spits out infinity, it's a symptom that our ultra-complex theories are incomplete, and our whole understanding of space and time has completely broken down.
We've seen how infinity constantly challenges our equations, our physics, and the very boundaries of our reality. It forces us to develop these ultra-complex workarounds just to keep our models from falling apart. And so, we leave you at the edge of the map with this final, provocative thought to ponder. Is infinity an actual physical reality out there in the cosmos, or is it just the exact place where human mathematics finally stops working? Thanks for exploring the limits with us.